Alright, this problem is slightly different. This one we're going to look at a spectral transition, which means we're going to move an electron between two orbitals. When we do that, we're going to use the Rydberg equation, which is given right here. It will be on your equation sheet, so it's just a matter of looking at it. So if we look at our transition, this will be in final, and the one will be in initial. So if we plug this in, we'll get the change in energy. It's going to be equal to minus 2.18 times 10 to the minus 18th joules over 1 over the final, which is 6 squared, minus 1 over 1, which is the initial, squared. Now, for simplicity's sake, I'm going to work just through this for a minute. So this basically is 1 over 36 minus 1 over 1, which when we do the math comes out to be equal to negative 0.97222. Now, if we go back and we multiply it by 2.18 times 10 to the minus 18th joules to get my delta E, okay, so I'm going to kind of put a line there so that we've done the work. Delta E comes out equal to 2.11944 times 10 to the negative 18th joules. At 3 significant figures, we'll get 2.12 times 10 to the minus 18th joules. Okay, now notice that we had a minus on a minus, which gave us a positive. The positive and the negative, or directionality, is positive because energy was absorbed, because we went from a lower energy level to a higher energy level. Okay, so calculate the wavelength in nanometers and the frequency of light of this transition. Okay, so in order to work this one, we need to know what the frequency of the light is. So we know two equations. Delta E is equal to hc over lambda, or delta E, or in this case just E, is equal to h nu. Okay, so easiest thing to do first is let's just do frequency. So we'll say 2.12 times 10 to the negative 18th joules is equal to 6.626 times 10 to the negative 34 joule seconds times nu. So nu is going to be equal to 626 e to the minus 20, no, minus 34. 2.12 e to the negative 18th. Alright, should come out to be equal to 3.1995 times 10 to the 15th. It's actually really a high energy. 3 significant figures, that would be seconds to the minus 1, so it's 3.20 times 10 to the 15th hertz for our problem. Now, I'm going to come up here. Let's solve for the wavelength. We know that E is equal to hc over lambda. So lambda is going to be equal to hc over E. Okay? Which again is 6.626 times 10 to the negative 34 joule seconds, joule seconds, times 3.00 times 10 to the 8th meters per second, divided by my energy level, which is 2.12 times 10 to the minus 8th joules. So my wavelength comes out equal to 9.3764 times 10 to the 8th negative 8 meters. I know that 1 meter is equal to 10 to the 9th nanometers, which gives me a value of 93.76 nanometers, which 3 significant figures is 93.8 nanometers. Remember, as the wavelength increases, the energy decreases. So as the wavelengths get smaller, this is a very high energy. So in all of this, we have answered A. Okay? So all of this is A. So B says, would light having a wavelength of 486 nanometers produce this transition? As the wavelength increases, energy decreases because they're inverses. Because as wavelength gets bigger, energy is going to get smaller. So when we look at lambda 486 versus lambda 93.8, both of these being in nanometers, this wavelength is much, much greater. So the energy associated with 486 nanometers is much, much less than the energy associated with 93.8 nanometers. So no, wavelength of 486 will not cause this transition. Now, if you want to go double check it, and you may do so, and I highly recommend you do that in homework, if we solve for E is equal to h nu lambda using lambda as 4.86 times 10 to the minus 7 meters, then the energy comes out equal to 4.09 times 10 to the negative 19th joules, which is much less than what we need, which is the negative 18, less than 2.12 times 10 to the negative 18th joules. So the question is asked, will this cause the transition? And the answer is no. Whether you do it by wavelength, whether you do it by energy, doesn't matter as long as you understand that one of them will explain the fact that this transition is not possible.